Hello, this is the Code Critics. In this episode, we are going to review a piece of code that computes the elements of a confusion matrix. First, a quick recap on what a confusion matrix is. Let's assume we want to assess the classification performance of a cat versus dog classifier. We have a trained classifier and some test images of cats and dogs. Instead of working with string labels, we usually work with numbers. Let's label cats with +1 and dogs with -1. That would be a common labeling for a support vector machine, for instance. We run the classifier over the images, and the predicted labels are +1, -1, +1, and -1. Now we compare those predictions with the target labels of the input images. For the first case, the classifier predicts the label +1, a cat, and indeed, the input image is a cat with label +1. We call this a true positive because we truthfully, correctly predict the positive case. In the second case, the classifier predicts -1, dog, but the correct label is actually +1. This is a false negative prediction. Similarly, for the third image, the prediction is wrong. But in this case, +1 is falsely predicted, while the correct label is -1. We have a false positive prediction. Finally, for image number 4, the classifier prediction and the target label agree. Both are -1, and we have a true negative prediction. Usually, the number of true and false negative and positive predictions are written down in a so-called confusion matrix, since it shows which class labels the classifier confuses when making predictions. In the given example, where we have exactly one case for each of the 4 different cases, the confusion matrix becomes 1, 1, 1, 1. This means that the classifier makes as many false predictions as it makes true predictions, and therefore has a prediction accuracy of 50%. Obviously, any useful classifier should perform better than chance, and we want to see high numbers for true positives and negatives, and low numbers for false positives and negatives. Here's an example of a classifier with a slightly better confusion matrix. The original code shown here computes the number of true positives for a list of true versus predicted class labels. This code is from an introduction into machine learning and has a very readable implementation. We zip the true and predicted class labels, and if they're both positive, we increment the counter for true positives. Easy to understand. If we run this code on the example data shown, we get the correct number of 4 true positives. Note that we use the number 0 instead of -1 for the negative labels. Both are fine. When training support vector machines, for technical reasons, typically the labels +1 and -1 are chosen, while for most other classifiers, 0 and 1 are more common, especially when there are more than just 2 classes. The other functions for computing the false positives, the false negatives, and the true negatives are almost identical to the computation of the true positives. I removed the comments to save some space. But as you can see, the only true difference in the implementation is in the comparison of the true and the predicted class labels. So while the code is very readable, it is also very repetitive. We surely should be able to find a more compact implementation. And here it is. We define a function conf that takes 3 parameters: targets, predictions, and case. I prefer the names tars and preds over y true and y pred. Since they are shorter, equally clear, express the plural and avoid the underscore. So how does this implementation work? As before, we zip targets and predictions, but here in a generator expression instead within a for loop. Furthermore, the comparison of the targets and predictions is implemented as a tuple comparison. If this comparison is successful, the generator produces a 1, and we sum all those ones up to get our confusion value. For the case parameter, we can define 4 constants that describe the true positive, false negative, and true negative case. Note that the tuple comparison and the constants are expressing the same comparison that was implemented as an if condition in the original code. To compute the true positives, for instance, we now can simply call conf with the constant tp for the case parameter. In summary, we have successfully replaced 4 functions, each with multiple lines of repeated code, by a single function containing 1 line of code and without any code repetition. The disadvantage is that the new code is a lot less readable if you're not familiar with more advanced Python constructs, such as generator expressions and tuple comparison. We can make the code more readable by creating extra functions using lambda expressions. The lambda expressions, however, reintroduce some redundancy, since the parameters tars and preds are repeated. This can be avoided by creating partial functions, but that again is a more advanced concept. The original code actually does not produce the confusion matrix, just its elements. However, with the new code, we can do this easily, using a nested list comprehension and our conf function. The new implementation has the additional advantage that it works for more than 2 classes, and the class labels don't even need to be numbers, but could be strings as well, since the conf function performs a tuple comparison. To summarize, there's a trade-off between readability and compactness. The original code is designed as a tutorial and more suitable for beginners. The revised code uses more advanced concepts, which makes it more compact and general, but also more difficult to understand. We have seen that the revised code works with non-numerical class labels such as strings, and also supports an arbitrary number of classes, not just 2. The main reason for the compactness of the revised code is that all code repetition was removed. While it is fine and common in tutorials to repeat code, it must be avoided in professional code. If you're interested in a public review of your code, let me know. And that's it. Thank you for listening.